So in this lecture, we'll be talking about some algebraic properties of matrices. So first, so far, what did we define? We defined the algebra, of course, the algebraic properties that we defined. Okay, so we have addition, okay, of two matrices. We can multiply a matrix by a constant, and we defined the product of two matrices. And as we said, the product of two matrices is not a natural operation. We have seen, for example, that AB may not be equal to BA. Most of the properties that we have, most of the algebraic properties of the real numbers are also valid for matrices. I didn't say all, because that's not true. So keep in mind, the main sticking point, the main problem is all the problems are with the product, because it's not natural. And because of that, it gets complicated. Okay, so what do I mean by this statement? For example, we have A time. I'm assuming, of course, that things can be done. For example, just to give you an idea here, I have three matrices, A, B, and C. In order for me to do B plus C, the size of B and the size of C must be the same. In other words, I mean the number of rows and the number of columns. But in order for me to do A times B plus C, is the number of columns of A must be equal to the number of rows of B, which is the same as C. So once it is possible, then what we have is A times B plus A times C. We cannot change them, huh? What's to the left is to the left, what's to the right is to the right, okay? Or for example, when you do A times B times C, okay? So for example, for this product, remember, in order for you to do B times C, the number of columns of B must be the same as the number of rows of C. And to do this operation, the number of columns of A must be the same as the number of rows of B. And and whether you do it this way or you do A times B and then times C is exactly the same. The end result is the same. Okay? What about if I multiply by a constant? Yeah, if you multiply by a constant times A times B, then is the same as C times A. In other words, you multiply A by the constant and then you multiply B, or it's A times C times B, okay, the little c, the little constant, okay, or C is a constant, etc., etc., okay? Okay, so now let us take an example remark, okay, and example, which shows how the product is very complicated, okay? So let us take A. Consider A equal 0, 0, 1, and 2, and B equal 0, 0, 2, minus 1. And let us take A times B. So what do we have? We have A times B. So this will be 0, 1, 0, 2 times 0, 0, 2 minus 1. So the first column of B, 0, 0, times anything will give me 0 and 0, okay? Because it's 0, 0, okay? Now what about the second column? That will give me the second column of the end result. 2 minus 1, the second column of B, time the matrix A. So we get 2 minus 1 times 0, 0, 0. Okay? And then when you take 2 times 1, 2. And minus 1 times 2, minus 2. So the end result will be 0, 0, 0, 0. So in other words, what we have is that A, which is not the zero matrix, B, which is not the zero matrix, and A times B is the zero matrix. A times B is the zero matrix. So this does not happen for real numbers. For real numbers, if two numbers are not equal to 0, their product is not equal to 0. Moreover, we have a matrix, identity matrix, okay, which is IN, is a square matrix of size n, 1 on the diagonals and 0 everywhere else. Okay, so if you take A, which is let's say, it doesn't have to be, in other words, I just need the number of columns of A, which is the same as the number of rows of IN, which is n. Okay, but that's fine. Let's just take a square matrix with size n. Then A times IN is so simple to see because we're going to take the columns of IN times A, and you will find that it is exactly A. Okay? And it's not only that, at the same time, if you take IN times A, you will find A. Okay? So not only you have A times IN equal to A, you also have IN times A equal to A. So for the products, IN behaves like the number 1 for the product of matrices, of course. Okay, it's like, we call it the unit. Okay, of course we don't have like the zero matrix, we don't have just one matrix. We have depending on the size, we have different matrices. Okay, and keep in mind, for example, just for the sake of, let's say example, I wanted just to show you this on a, but if you take on the example A, which is a 2 by 3, A, B, C, D, E, F, and we take, in order for me to do A times I am gonna consider the I3. Okay, 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay, so if you take A times I3, you will find A. But we cannot do, this does not make sense. This does not make sense. Because I3 has 3 columns and A has only 2 rows. So you need to have the same number. The number of columns of I3 should be the same. Sorry, the number of columns of A should be the same as the number of rows. Hold on. So this will be what? This will be 3. Okay, this matrix I3 is 3 by 3, and this one is 2 by 3. So we cannot do the product because, as I said earlier, the number of columns of I3 is not the same as the number of rows of A. Okay, so this product does not make sense. So we can have one side but not on the other. But if A is a square matrix, then the problem is easy, and we can consider. Okay, next I want to talk about something in perspective of what we did before with the row echelon form and reduced row echelon form. So let's, here we have a beautiful result. Of course, here I'm looking at the row elementary operations on a matrix. Has nothing to do with system here. So let us start with an let A be a square matrix. Okay, and let us do the row elementary operations. Apply to A. Okay, apply to A. Then we can go down to get the row echelon form, but I don't want that. I want to go up also to get the reduced, okay, row echelon form. So remember, on the first non-zero on any row is 1, and above it, below it are all zeros. Okay, so now what is the shape of that matrix? Okay, so if the matrix A has size n, then this new matrix, the reduced row echelon form, let's call it R. So this R will be something like this. And what's interesting is also square matrix with the size n. What's interesting is we have two options, huh? Two options. Either we have at the bottom zeros, or not. So either we have 0 rows or we have no 0 rows. Okay, so if R has no 0 rows, so what happened? As we said, here is your R, and if you take any row, the first non-zero will be 1. Yeah, so you have zeros here, and above it zeros, and below it zeros. So you see, as long as you don't have a row of zeros, then that's what's going to happen to us. Okay, like this, the shape. So the idea here is what? Okay, is that in fact we can show in the case of the reduced echelon form, it has what? Only this form. Okay, and in this case R is the identity matrix. So if we don't have any row with zeros, at the end what you get when you go up and down, okay, down first and up after that using the row elementary operations, what you end up having is the identity matrix. This is very important later on when we try to find a way how to compute the inverse of a matrix. Okay, so this point is very important. Okay, let us continue more with the some of algebra properties and identities. So some algebra identities. So for example, okay, we know, okay, that A plus B squared is A squared to AB plus B squared. That we grew up with. Okay, so what happened for matrices? What happened if I take A plus B squared? So we are tempted to have A squared plus 2AB plus b squared. So we are tempted, huh? So that's the question, okay? So in other words, why I'm making this point is that sometimes the people will just use the natural algebra identities on the real number, and they want to have them as well for matrices. Okay, so let's find out, okay, what happened in this case. Okay, so we have a plus b. Let's find out if that's the case. So this is clearly a plus b times a plus b. And now let us use the distributivity properties that we said they are valid, and this will become a plus b times a plus b times b. So remember, we know what's to the left stays to the left, and what's to the right stays to the right, okay? So we have then a times a, b times a times b, and b times b. A squared, b times a times b, and b squared. So when do we have this the same as this? Okay, so this happens if and only if, in other words, we have that identity if b times a is equal a times b. We call them commutative matrices. Okay, so if BA equal to AB, then the formula is true. But if BA is not equal to A times B, the formula is false. Okay, so what happened now when we deal with something very simple, which is the same matrix? We take the product of the same matrix. So we'll start a to the power 0 equal the identity matrix. We're talking about the square matrix, by the way. Huh? So a to the power 0 equal I. And then we have a, and then we keep multiplying, okay? So we have a to the power 1 equals a to the power 2 equals to a times a to the power 3, which is a to the power 2 times a, etc. So this way we can define a to the power n for n equals 0, 1, 2, etc. The problem is how to evaluate a to the power n. So in general, this is an extremely hard problem, okay? And there are examples where you need to evaluate a to the power n, okay? So for example, if you want to define something called the functional theory of matrices, like what about exponential of a matrix? Can we define ln of a matrix? Sine of a matrix, cosine of a matrix, okay? Can we define this? So we can use calculus to help us see how we can approach this problem. But anyway, all of them, they involve what's known as the power series, and they involve the computation of the powers. So later on, we'll see with the help of the, for some special matrices, what we call diagonalizable matrices, there is a way of how to do that. But otherwise, in general, it's very complicated. It's very complicated. So let me give you an example, something interesting. So here, example, but in fact, is a little bit more than an example. You can look for it on Google, Cayley-Hamilton result. So Hamilton, both of them, they were in the 19th century, around 1800 and something, and they both worked on matrices, and especially Hamilton, he worked on the quaternions, special type of matrices, and they worked together and they came up with something very interesting, beautiful, by the way. So this explains when I said about the inner working of matrices. So now it's really about matrices, has nothing to do about systems. It's about matrices, the inner working of this two-dimensional array of numbers. So to give you a flavor of this Cayley-Hamilton result. It's a beautiful result. Let A be equal to -1, 0, 2, and 3. Okay? So let us compute A squared minus 2A minus 3I2. Okay? So first let's go by A squared. So 0, 2, 3 times -1, 0, 2, and 3. So we take the first column, which is -1, 0, times the two matrices. -1 times -1, that's 1. 0 times 2, 2, so it's +1. And if you look at the second one, -1 times 0, 0 times 3 is 0. And then 2, 3 times -1, 2. 2 times -1, -2. 3 times 2, 6. Add it, 4. And 2 times 0, 0. 3 times 3, 9. Great. So now what do we have? We have 1, 0, 4, 9, minus 2 times -1, 0, 2, 3, and minus 3 times 1, 0, 0, 1 equal. So what do we have? We have 1, 0, 4, 9 plus -2 times -1, 2, 0, -4, -6, plus -3, 0, 0, -3. Okay, so 1 plus 2, okay, this will give me 3 minus 3, 0, 0, 0, 0, 0, 4 minus 4, 0, plus 0, 0, 9 minus 6 minus 3, 0. So what we have is that A squared minus 2A minus 3I is equal to a 0, 0, 0, 0. Okay, so this is very interesting. If you look at there is something behind this. This is just a simple example, but in fact something very interesting, which is if we consider set P of x to be x squared minus 2x minus 3, and consider now P of A to be a squared minus 2 times a to the power 1 minus 3 times a to the power 0, which is I. Okay? So, and you can see that this is equal to what? To 0, 0, 0, 0. This is the famous Cayley-Hamilton theorem, okay, which has some amazing applications, okay, amazing applications. One of them, let us just, so let me show you now. What is a squared? From this, knowing this, so what is a squared? Is equal to a plus 3i. Yeah? So what about a cubed? So it's gonna be 2a squared plus 3a times I, a. But we know what a squared is gonna be 2 times 2a plus 3i plus 3a equal 2 times 2, 4, plus 3, 7, and 2 times 3, 6, 6i. So as you can see, we can easily show that any a to the power n is in fact some number times a plus some number times I. So you see, here's an example, beautiful Abigail, where you get all the powers, okay? Okay, more, we can say more than that, okay? Another way to see it. This time, I'm gonna take 3i2 to the other side, okay? So we have a squared minus 2a equals 3 I2 plus 0. Okay, so let me factor out A because everything works fine here. A times A minus 2 times I equals 3I2. So if I take B to be 1/3 times A minus 2I2, then what we have is A times B is equal to what? 2I2. And both of them commute, as you can see, because A and B, they commute, I2. In fact, we do have also B times A, which is also equal to what? To the identity matrix. Okay? Before I close this part, let me look at the algebraic properties of the transpose of a matrix. So what do we have? Some of them are very easy, huh? So I don't want to. So what happens if you take the transpose of the transpose? So remember, if A is a square matrix, the transpose is just a reflection with respect to the main diagonal. In general, you just interchange between the rows and the columns. So you do it once, you do it another time, you come back to your matrix. So this gives you the matrix A. Okay, what about A plus B transpose? So this will be easy to show that it's A transpose plus B transpose, 3. What about if I have a number times a matrix and I do the transpose? Okay, the C times A will multiply all the entries by C, all of them. And when you multiply all of them by C, then it stays there. You take the transpose and then you can take it outside. So in fact, what happened is just C times A transpose. The hardest one is this one. What is the transpose F? A times B. Okay, so this is a little bit tricky, not that hard. Of course, let me just tell you it's B transpose times A transpose. Okay, and it's very simple to see a little bit why. It's not easy to prove, but let me tell you that's not A transpose times B transpose. It will not be. Why? Because, remark. So what happens if I take 2 times 3 2 by 3 times 3 by 5, for example. So we know that the end result will be 2 by 5. Okay, it's the product, huh? Now what about if I take the transpose now? Okay, so if I take the transpose, 2 by 3 transpose and 3 by 5 transpose, this will give me what? 3 by 2, and this is 5 by 3. So A times B transpose, this will never be, in this case, A times B transpose will never be equal to this because it does not make sense to do the product to start with. So this does not make sense, does not make sense. But as I said, it's not like hard to do. It's just complicated a little bit more than the other ones. But anyway, the result is that you have to switch them. It's B transpose times A transpose.